We left off looking at the rather interesting shape of cyclohexane. And as you recall from a previous class, the stable conformation of cyclohexane is a structure we call the chair conformation. And you can see it here if you think of this as kind of a lazy boy recliner. This is the headrest. Here is the seat. This is the footrest. What this shape does is essentially remove all elements of strain from cyclohexane. There's no significant steric strain, no significant angle strain. There's also no significant torsional strain, and one can see that if you imagine kind of standing here to the left of this chair conformation and looking at it from the direction indicated by these two arrows, we get a Newman projection that you can see here. So here's the headrest. We're standing behind the chair. The seat is essentially along here, and the other side of the ring we can kind of think of as the footrest. This is a ball and stick model in that same orientation. And when we look at that, you can see that we have fully staggered bonds around these bonds along the sides of the chair. We could rotate the chair and look down other bonds. So for instance, we could look down this carbon-carbon bond, this one parallels it, and we would find the same thing. Another curious thing that we discovered is that in this chair conformation, we have bonds to hydrogens that extend in different directions. And there's some terminology associated with this. These hydrogen bonds to hydrogen that extend up and down are referred to as axial bonds. And the notion here is that there's an imaginary axis that passes through the center of the ring, kind of in this fashion. And those bonds are parallel to that vertical axis. These other bonds, illustrated here with the hydrogens in green, extend outward from nominally what we would think of as the plane of the ring, even though the ring isn't planar. And these are known as equatorial bonds around there because they seem to extend outward from the equator of the structure. So cyclohexane isn't conformationally static. It can undergo a change in conformation. And one of the simplest things that can happen first is that one part of the ring kind of flips up or down. So you could imagine taking that chair conformation and kind of flipping up what we think of as the footrests kind of up into another headrest. And you get a conformation that looks like this. You could build this with your model kit. And it has a name. It's known as the boat conformation. But this is actually not a stable conformation. This is a transition state that the molecule is going to pass through. So the boat conformation is a transition state. So it's a transition state in that there can be an additional change in shape that can kind of relieve some of the strain that's present in this structure. If we look at the ball and stick model over here, particularly along the sides, we have eclipsing bonds. For instance, this carbon-hydrogen bond and this carbon-hydrogen bond, these are eclipsed. We also have a problem in that these hydrogens here are depicted in red. These are known as the flagpole hydrogens here and here, kind of on the bow and the stern of a boat, if you will. They're very close together. And so this structure has a relatively high energy compared to the chair conformation. It's about 6.4 kilocalories per mole higher in energy. But as I said, it's not a stable structure, it's a transition state. Because what happens is once it flips into this shape, you get a slight twisting. And that slight twisting of the two ends relieves some of the torsional strain. And so this is the stable alternate conformation for cyclohexane. And by stable, I mean it lies in an energy minimum on a potential energy curve, but it's not the overall energy minimum. The chair is. So this is known as a twist boat. You'll notice here that we've relieved some of the strain. About a kilocalorie per mole of the strain has been relieved. And you can kind of see that in these structures that you see here, these ball and stick models. You can see that the whole thing has been kind of torqued or twisted. And if you turn this and look down the sides of this, you can see that we've relieved some of the torsional strain. These bonds look a little staggered now. The other thing, which isn't quite as obvious, is these two hydrogens have moved a little bit further apart. So some of the steric strain, some of the torsional strain has been relieved. So if you imagine this change in shape occurring for this molecule, you want to think about this as uh, happening in a kind of a series of steps, if you will. So one of the things you can imagine with our chair conformation, so here's our chair conformation. Think of this as the headrest with carbon number 6 here at the top of the headrest, and carbon number 3 down here at the bottom of the footrest. You can imagine interconverting this by flipping up the footrest so that it's up into kind of a headrest position, and then correspondingly flipping down the headrest so that it makes a new footrest. And we can see this over here to the right, the other structures. So this is also a chair conformation, but you'll notice now this carbon number 6 is pointed down in what we think of the footrest position, and carbon 3 now is up. So this is known as ring flipping or chair-chair interconversion. And there's a relatively low activation energy to this process, just about 10.8 kilocalories per mole. And because there's so much energy available at room temperature, that low energy barrier means that this interconversion is happening very, very rapidly, roughly once every 100,000th of a second, this sort of ring flip, back and forth, back and forth, back and forth at room temperature. If we map this whole process out, it's a little more complex than it appears here. It's not just a simple matter of flipping up carbon number 3 and flipping down 6. It's a little more complicated than that. And so here it is kind of mapped out on a potential energy diagram. So we have one chair orientation here on the left as our global energy minimum. And you'll notice carbon number 4, I want you to pay attention to carbon number 4 and carbon number 1. And then over here is the other chair conformation. And now you notice that carbon number 4 is pointed down in this orientation and carbon number 1 is up. So how do we get from here to there? And the answer is the process that you see here. So the first thing that happens is what I had mentioned before, which is essentially the footrest begins to move upward. So in this case, that means carbon number 1 moves up. And that brings us to the highest energy of this, the reason for the activation energy of about 10 kilocalories per mole. And that's this structure. This is known as a half chair. This is a transition state, not a stable structure. There's a great deal of strain now because of the planarity of these 4 bonds. We get a significant amount of torsional strain. We also generate some angle strain because by flipping up the footrest, you have to kind of open up the ring and open up some of those bond angles from tetrahedral to about 120 degrees. But as soon as that moves upward, carbon number 4 can come upward. That would get us into, it would drop into a twist boat conformation. Now, the twist boat conformation actually exists in 2 different forms, and that would happen by twisting the ends of the boat relative to one another. So essentially, we're kind of moving this end of the boat out of the plane and this end of the boat into the plane and kind of giving it a torque. And so there are, in reality, 2 different twist boat conformations that represent relative energy minima. But you can then continue on through a different half chair. Notice the numbers. And then that would fall into our other chair conformation. So it is a bit more complex than it appears, but the overall activation energy, you notice here, is only about 10 kilocalories per mole. And with there being more than 20 kilocalories per mole of energy available at room temperature, this is easily overcome. And so the molecule can flip back and forth and back and forth. One of the consequences of this is that anything attached to the ring is going to kind of swap positions from axial to equatorial. So we look closely here at this example where we have these placeholder atoms, X and Y. In one chair conformation, we can see that Y lies in an axial position on the ring and X lies in an equatorial. And now if we imagine that ring flipping occur, remember how that happens, that kind of the footrest moves upward. That means that other positions on the ring correspondingly move downward. And so these are going to swap positions, and the chair interconversion is going to move this X from the equatorial into the axial position, and the Y is going to flip down into the equatorial position. I encourage you to build a model kit and kind of twist your model kit so you can see this happen. Now, another consequence of this chair-chair interconversion with a substituent on the ring that isn't hydrogen is that you can then bias these chair conformations such that one chair conformation is significantly more stable than another. So here's an example of that. This is methyl cyclohexane's two chair conformations. And below, what you see are the experimentally measured proportions of these chair conformations that exist at room temperature. So at room temperature, this chair conformation with the methyl group in this equatorial position makes up about 95% of the mixture. And this chair conformation with the methyl group axial makes up only about 5%. Now that said, there's still a relatively low activation energy to interconversion. It's just that if you could somehow take a snapshot of a collection of molecules, you'd find that there would be 95 of these structures for every 5 of those that you found. So these percentages tell us that this is, for some reason, more stable than the structure over here where the methyl group is axial. Or the way organic chemists like to think of it, there must be some component of strain that's present in this conformation that makes it less stable than this one. So let's see if we can kind of tease out what's going on there. And before we do that, let's look at these numbers. So we have two conformations in equilibrium, and we have a 95 to 5% ratio between those. This is a simple free energy relationship, and we've seen this diagram before when we think about conformations. But on this diagram, if we pick out a 95% more stable isomer, we would find this data point on our graph. And if we then extrapolate that down, we can determine, or estimate, I should say, the free energy difference between those two structures. It turns out to be about 1.7 kilocalories per mole. Now, that's a very small number in the grand scheme of things, but that's a large enough number that you get a 95 to 5% mixture. All right, so what's going on? Why is the axial methyl less stable than the equatorial methyl? And that's illustrated here. In the stable conformation, there's not really any significant elements of strain. There's no steric strain to speak of. These hydrogens, for instance, are very far apart, far enough apart there's no interaction between their electron clouds. The methyl group can freely rotate and adopt a staggered conformation around this carbon-carbon bond. The ring is in a chair conformation, so there's no significant angle strain, torsional strain, or steric strain. But in the other conformation, where the methyl group moves into this axial position, we have a very particular type of steric strain that arises. So the reason that the minor conformation is the minor conformation is this, and that's right in here, that methyl group now, when it's in the axial position, places its hydrogens in close proximity to these neighboring hydrogens. We have a name for this. It's a particular type of interaction, steric interaction, that commonly arises on cyclohexane rings. and it's called a 1,3 diaxial interaction. And the reason for that is that this group that's axial we would indicate as being on carbon number 1. And the steric interaction is happening between that group and the hydrogens on carbon number 3. And so the group on number 1 is interacting with the group on carbon 3. And as I said, this is a small amount of steric strain. This 1.7 kilocalories per mole is a tiny number, but nevertheless, that's all it takes to get this big bias between these two, such that you have 95% of this at room temperature. You can see this steric strain a little more closely if you have the ability to generate space-filling models, and here we have those. So our ball and stick model you can see here on the left. This is what we were looking at. We're interested in the hydrogen here on the methyl group interacting with these hydrogens in this kind of 1,3 interaction, so that there's some steric interaction between those. You can kind of see it in the ball and stick model. He's shown here in the center. So these are the hydrogens of interest. And again, we're getting some steric interaction between those. But the space filling model is much clearer. So if we look at the space filling model, here's where those hydrogens are interacting. And looking, if you look down from above on this structure, so if you were standing up above this space filling model and looking down on top of it, you can see that here, that this hydrogen is bumping into these hydrogens here. And that's that small amount of steric strain. It's worth looking at the same sort of models of the more stable conformation, and that's what you see here. So here's this conformation where the methyl group is in the equatorial position. Here's a ball and stick model of that. And if you look at the two space filling models, you can see that in these space filling models, there's actually a gap here between these hydrogens. And so that methyl group that's off to the side is interacting with the neighboring hydrogens. We see the same thing here. There's a gap between these. We can see the carbons in between. So there's not any significant steric interaction between those. So this is a structure that's relatively strain-free. So it really comes down to size of the substituent. What caused the strain was the sheer size of the methyl group. So if you have something other than a methyl group on the ring, you're also going to get a bias, but the amount of bias you get between the two chair conformations is going to come down to the steric size of the group. So here's just a few examples that kind of illustrate that. So at the top, we have fluorocyclohexane, and here in green is a fluorine atom. And a fluorine atom is significantly larger than a hydrogen atom, but significantly smaller than a methyl group. Nevertheless, that size is enough that when the fluorine is axial, look at the ball and stick model here, when that fluorine is axial, it's going to bump into these hydrogens that are in that 1,3 relationship, and we can kind of pencil those in. That fluorine has a little bit of interaction. The ratio of the two conformers is the equatorial fluorine is 60% of the mixture. The axial is that. So if we go back to our graph and we look that up, that's only about 1/4 of a kilocalorie per mole difference. The second example that we see here is an isopropyl group. Here we have an isopropyl group, and that one is only slightly more than a methyl. It's about 2.1 kilocalories per mole. You notice we've only changed that proportion here slightly. We're now at 97%. And that's because the isopropyl group can kind of swing out of the way, most of it. And so it's kind of mimicking a methyl group. Look at the ball and stick model over here. This is the isopropyl group. And it's oriented in such a way that only one of the hydrogens is interacting with these neighboring hydrogens over here. So those hydrogens are here, and we get a little bit of steric strain. Now, contrast that with our last example where it's almost difficult to measure. This is essentially a molecule that lives only in this conformation and none of it with the axial. This is a T-butyl group. And you can see in the space filling model just how big a T-butyl group is. So this is the T-butyl group in these molecules. They're really quite large. This is the T-butyl group you see here. And in fact, it's a little hard to see with the space filling model, but that group is so large that the bond doesn't really stand straight up. The bond kind of sticks out at an angle. So that carbon-carbon bond, this carbon-carbon bond that holds the T-butyl group is actually angled over this way. So the big size of that T-butyl group is biasing that reactions and such that we get this very large energy difference between the two. You could look at many other examples of these. Here we see many groups. Fluorine we looked at, methyl, here's our isopropyl. We get those numbers. Here's the T-butyl group. These are the other groups. And it's all a reflection of the steric size of those groups. The smaller groups have relatively small energy biases. The large groups, relatively large energy biases.